there are two parameters, mu and sigma square. So we showed that mu is the mean and the variance is sigma square. We also showed that all odd ordered central moments are 0. Even ordered moments, when we look at, so fourth central moment was 3 sigma to the power 4, and therefore the measure of kurtosis was 0. So that is why when we say normal peak, actually it is the peak of the normal distribution. Okay. Now let us look at other properties of the normal distribution. So we start with the moment generating function. So moment generating function is expectation of e to the power tx. Somebody is having some problem. Srijan Das. Okay, yeah. So this is minus infinity to infinity e to the power tx 1 by sigma root 2 pi e to the power minus 1 by 2 x minus mu by sigma square dx. And you remember the transformations that I have done in the last class? What was the transformation? Z is equal to x minus mu by sigma. So dz is equal to 1 by sigma dx. And also it will mean that x is equal to sigma z plus mu. Okay, this is the transformation that we had considered. Do you remember this?
Yes, sir.
So if you substitute this here, you will get 1 by root 2 pi e to the power t sigma z plus mu minus z square by 2. Okay, so what we do, we adjust this term which is there in exponent and we write it as minus infinity to infinity 1 by root 2 pi e to the power minus 1 by 2 z minus sigma t square dz and e to the power mu t plus half sigma square t square. So what we do in the exponent, this z square by 2 minus sigma t z term is there. So here I take half common and I complete a perfect square here. So I add and subtract half sigma square t square. So this becomes a perfect square and I get e to the power minus 1 by 2 z minus sigma t square. And then remaining terms are, of course, e to the power mu t comes out, and I have added e to the power half sigma square t square, so that also comes out. So this is the thing. Is this adjustment clear? Now you look at this one, this term, what it is. It is integral of a term which looks like a density of a normal distribution, because it is 1 by root 2 pi sigma. If you put 1 and mu you take sigma t, then it is nothing but the density of a normal distribution. So it is the density of a normal distribution with mean sigma t and standard deviation or variance 1. So this will integrate to 1. Okay. So within the integral, we have PDF of a normal distribution with mean sigma t and variance 1. So the value of the integral is 1. So we get moment generating function as e to the power mu t plus half sigma square t square. So is this derivation clear?
Yes, sir.
Yes, sir.
Now we prove the linearity property of a normal distribution. Okay. So what is the linearity property? Let X follow normal mu sigma square distribution and y is equal to ax plus b, then y also has a normal distribution with mean a mu plus b and variance a square sigma square. This is called the linearity property of the normal distribution. The mean is transformed by the linearity term, and the variance, or you can say the variance gets multiplied by the multiplicative term here, that a square. So to prove that, actually we will make use of the moment generating function. Yes. Is there any question? Ramit Kumar. Do you have any question? So MYT, that is expectation of e to the power ty, that is expectation of e to the power t ax plus b. So this is equal to e to the power bt, expectation of e to the power atx. So this you can consider as the moment generating function of x at the point at. Okay, this is the moment generating function of the random variable x at the point at, because expectation of e to the power tx is mxt. Now moment generating function of x is known because x is a normal distribution with mean mu and variance sigma square. The form of mxt is e to the power mu t plus half sigma square t square. There you replace t by at. So this will give you e to the power bt, e to the power mu t, that is mu into at plus half sigma square t square, that is at whole square. So you write down these terms. It is e to the power a mu plus b into t plus half a square sigma square into t square. This is moment generating function of a normal distribution with mean a mu plus b and variance. So by the uniqueness property, we conclude that y follows normal a mu plus b a square sigma square distribution. So this is the linearity property of the normal distribution. Is the proof clear to everyone?
Yes, sir.
Now you can make use of it, and using this we can conclude that if x follows normal mu sigma square, then z is equal to x minus mu by sigma. This follows normal 0 1, because here you substitute a is equal to 1 by sigma and b is equal to minus mu by sigma. So a mu plus b becomes 0 and a square sigma square becomes 1. This normal 0 1 is called the standard normal random variable or standard normal distribution. Okay. So let us look at more of the properties of a normal distribution. So what will be the probability density function of Z? The PDF of Z is, we will use a slightly different notation. So we use a small phi notation. Okay. 1 by root 2 pi e to the power minus Z square by 2. Z is from minus infinity to plus infinity. So this is the probability density function of a standard normal distribution. 1 by root 2 pi e to the power minus Z square by 2, because mu is 0 and sigma is 1. Okay, if you look at the plot of this, you can see that this is symmetric about 0. Okay, so the cumulative distribution function of standard normal distribution is denoted by capital phi. Okay, the CDF of Z is capital phi of Z, that is of course minus infinity to Z phi t dt. Okay, this is the CDF of the standard normal distribution. Because of the symmetry, you can actually see some property also. Suppose I put this value as minus a, this is say plus a, then this probability is same as this probability. Or if you look at this probability, then this is same as this probability. Okay, from this you can conclude then, due to symmetry of PDF about 0, we get that phi of minus a is equal to 1 minus phi of A. From this diagram you see this. If I consider phi of minus A, that is this probability, this is same as this probability on the right side of A. So this is nothing but 1 minus phi A. So this is the property that we get for the CDF here. Okay. This means phi of A plus phi of minus A is equal to 1. Okay. In the standard normal CDF, you get this property. And of course, phi of 0 is equal to half. Because 0 is the median here. Now, this transformation, because if I have any normal distribution, I can transform it to the standard normal distribution. Due to this, we can actually use it for calculation of the probabilities of a normal distribution. See, when we get the integrals of exponential distribution or gamma distribution, beta distribution, etc. So we use the functions there, okay, whatever incomplete gamma function, incomplete beta function, etc. When you get normal distribution, then this is slightly more complicated also. So it has to be done using numerical integration only. So therefore, this property of symmetry is very useful because the tables are then given only for one-sided. Okay. So if we want to calculate the probabilities of any normal distribution, then we transform it to standard normal and we calculate it. So we can use for evaluating let us say x follows normal mu sigma square, okay, and we want to calculate the probability of a less than x less than or equal to b. That is probability a. Of course, this less than or equal to, it doesn't matter because it is a continuous distribution. So we write it as probability x less than or equal to b minus probability x less than or equal to a. So this is nothing but probability of x minus mu by sigma less than or equal to b minus mu by sigma minus probability x minus mu by sigma less than or equal to a minus mu by sigma. So this is nothing but probability of z less than or equal to b minus mu by sigma minus probability z less than or equal to a minus mu by sigma. That is phi of b minus mu by sigma minus phi of a minus mu by sigma. So the probabilities related to any normal distribution can be evaluated using the tables of the standard normal distribution. Okay. Is this point clear?
Yes, sir.
Let us look at some more properties now of this standard normal. So if you see here, this is the form of the probability density function. Since you have e to the power minus z square by 2, you can easily understand that as z increases on either side, that is on minus side or plus side, the density approaches 0 very fast. Okay, so that means there is a huge concentration of the probability in the center of the distribution. So let us look at from the point of view of a standard normal table, and then let us look at the interpretation for the general normal distribution. Okay, so let us see. Let Z follow a normal 0, 1 distribution. Okay, so any of you, if you have any other device, you can easily see the tables of standard normal distribution. Okay, it is given in every book of statistics. If you see towards the end, the tables of the standard normal distribution are there. So you just look at certain important things there. Okay, so for example, you will see that phi of 0 is half. That means the probability up to 0 is half, which is true, of course, because of the that it is the median. Then let us also look at phi of 1. Phi of 1 is 0.8413. If you want to write for a few more decimal places, you can do that. I am just writing 4 decimal places because for explaining that is enough for me. Let us also write few more values. Phi of 2, for example, phi of 2 is 0.9773. Then phi of 3, let me write. Phi of 3 is 0.9987. Okay, just I am writing this one. You can write more also, but usual normal tables will be if you just check there, it will be given from -3 to +3. In fact, they will tabulate only 0 to 3 because the other side you can calculate directly by using the relation phi of -a plus phi of +a is equal to 1. So other side you can always calculate. Okay. So if you see any standard normal distribution table, these values you can easily see. Now why I have written this, just to give you some sort of idea about the concentration of the probabilities. So let us look at, suppose I want to write what is the probability -1 less than z less than or equal to 1. Okay, what is the probability that mod z is less than or equal to 1. Okay, so this is phi of 1 minus phi of -1. And if I write phi of -1 as 1 minus phi of 1, then this is nothing but 2 times phi of 1 minus 1. Now phi of 1 just now I have written, it is 0.8413. So what value I will get? I will get 0.6826. So it means that -1 to 1 you have 68% of the probability. See, I am saying the range of the distribution is -infinity to infinity, but because the tails approach 0 very rapidly, there is lot of concentration in the center part. So -1 to 1 itself contains 2/3 of the probability. Let us look at the second part, -2 less than or equal to z less than or equal to 2. That is phi of 2 minus phi of -2. Again, because of this relation, it becomes 2 times phi of 2 minus 1. And phi of 2 I have written here. So you can easily calculate and tell me the answer. It is how much? 0.9987. Tell me.
9546.
95. That means from minus to 2 you have more than 95% of the probability. Let us go further. Let us see minus 3 to 3. So by the same argument, it is 2 times phi of 3 minus 1. And what is phi of 3? 0.9987. So what is the value?
0.9974.
Which means 99.75% of the observations lie between minus 3 to plus 3. Okay. Now let us use this relation that a minus x less than or equal to b, a less than x less than or equal to b is phi of b minus mu by sigma to phi of a minus mu by sigma. So if I convert this, so if x follows normal mu sigma square, then probability of mu minus sigma less than or equal to x less than or equal to mu plus sigma, that is 0.6826. Probability of mu minus 2 sigma less than or equal to x less than or equal to mu plus 2 sigma, that is 0.9546. And probability mu minus 3 sigma less than or equal to x less than or equal to mu plus 3 sigma, that is equal to 0.9974. That means almost 99.74% of the observations, they lie within 3 sigma limits. Now these are, this is very powerful result, and it gives a very strong interpretation of the normal distribution. So generally then what happens that when we look at the industry, in the industry we are looking at the specification limit. So for an example, any product, okay, if you are considering any product, so you look at, say, for example, this pen, okay. So if I have this pen, so there are several parts of it. So for example, you look at that there is a cap of the pen, okay, there is a cap of the pen which should fit in exactly like this. So there is a inner diameter of the cap, there is an outer diameter of the surface here, okay. So it should be exactly in the way that it should fit in, otherwise see either it will be too loose or it won't fit in here. If either of the things happen, then the product is of not use to the market, okay. So the industry has to put the specification on the diameter because it is produced using a mechanical production unit. So every product or every unit that is produced, it should lie within 3 sigma of the specified diameter, that is mu minus 3 sigma to mu plus 3 sigma. If it is beyond that, then the product is rejected. So the quality control engineer, he will put the specification limit as 3 sigma limits, okay. So same thing is true for everything, which is done in the industry. They, of course, now there is a concept of even higher. So basically, if we say 3 sigma limit, what does it mean? It means out of 10,000 produced items, 26 items are likely to be rejected because you have 0.9974. So 26 observations are likely to be rejected out of 10,000 produced items. So of course, some of you will be going to internships in the industries, especially say manufacturing industry or FMCG industries. There you will see that there is a total quality control department. So there is an assembly line where product is coming out, for example, say a shampoo bottle or a hair oil bottle or a cream, okay, and then you will see that the product is coming out, and after every 100 they will take out one thing for sampling. They will check whether the specifications are okay or not, and then they will check from there that, so in a particular day, say maybe 1 lakh items are produced. So that means they would be checking something like 1,000 items. So out of 1,000 items, then they will see how many of them they meet the specification. So if more than say 997 meet the specification, then they will say that the production process is okay. Otherwise, they need to adjust their production process. Okay. Of course, now there is a concept of even more, because if you consider, say, medicine or where it is involving, say, life of a person, then even this one is not that good. Like if you say 26 persons out of 10,000 persons, they do not get treated by a certain particular treatment, then this is not good. So then they go, nowadays there is a concept of 6 sigma limit. So 6 sigma increases this accuracy even more. So anyway, I will not talk about that thing at this point of time. Okay. So is it clear to you? Is this discussion about the limits of a normal distribution, is that okay? Is it clear?
Yes, sir.
So let me just take up 1 or 2 examples and then we move ahead. So a distance runner completes a race of a 1 mile, okay, and the time is, so every time when he will run, he will take different timings. So that timings have been modeled as a normal distribution with mean 241 seconds, that is 4 minutes 1 second, and standard deviation 2 seconds. Okay. What is the probability that this runner will take, say, less than 4 minutes, or say more than 3 minutes 55 seconds? Okay, so these are some of the questions that we are posing based on this normal distribution. Okay. So the first question is, what is the probability he will complete in less than 4 minutes? That is, x is less than 240. So we will use the transformation to the standard normal. So this becomes probability z less than 240 minus 241 by 2. That is probability of z less than minus 0.5. So as I mentioned, you just see the tables of the standard normal distribution. This value is 0.3 3085. So that is nearly 30% chance that he will complete the race in less than 4 minutes. Okay. Similarly, let us look at the second part. What is the probability that he will take more than 3 minute 55 second? So 3 minute 55 second becomes 235 seconds. So now if we convert to Z, then this becomes greater than 235 minus 241 by 2. That is probability Z greater than minus 3, which is same as probability Z less than 3, that is phi of 3. Phi of 3 just now I wrote, that was 0.9987. So there is a more than 99% chance that he will complete the race in more than 3 minutes 55 seconds. Is the solution clear? Could you follow the solution?
Yes, sir.
Let us take up another problem. Suppose the NAV is actually net asset value. In the stock market, this is used of a share is a normal random variable with mean, say mu is equal to say 10 and say sigma is equal to 0.25. Okay. What is the shortest interval that has probability 0.95 of including okay. So due to the nature of the normal distribution, the shortest interval will be symmetric around the mean. Okay, the shortest interval will be symmetric about mean. So suppose this is the mean 10. So it is something like 10 minus a to 10 plus a. Because if you want to have a certain probability with the shortest interval, then it should be symmetric around the mean because of the nature of the normal distribution. Okay. Due to the nature of the some student is trying to take control of this one. I think you have clicked some button. Who is that? See, there is some icon being shown on my screen that give control, stop presenting. So who is that? Please remove this icon from here. Some student is using some control there in MS Team. Please remove this one from here. Who is that? Okay. So due to the nature of the normal distribution, the shortest interval will be symmetric about the mean. So let us take the interval. Ten minus a to 10 plus a. So probability that 10 minus a is less than or equal to x less than or equal to 10 plus a. So what we want this probability to be 0.95. Okay. We want this probability to be 0.95. So we make it x minus 10 by sigma, that is to convert it to the normal standard normal distribution. So we are getting 10 minus a minus 10 by sigma less than or equal to x minus mu by sigma, that is 10 basically. Okay, let us 10 plus a minus mu by sigma. So here in this distribution, see mu is 10 and sigma is 0.25. So let us substitute that here. So if I put mu is equal to 10, then this gets cancelled out and you get probability minus 4a less than or equal to z less than or equal to 4a is equal to 0.95. That is 2 times phi of 4a minus 1, that is 0.95. Because phi of 4a minus phi of minus 4a. So phi of minus 4a I will write as 1 minus phi of 4a. So it becomes 2 times phi of 4a minus 1. So this gives me phi of 4a as equal to 0.975. So now you see the tables of the normal distribution. What is the point up to which you get the probability 0.975? So the table of the standard normal distribution gives this point as 1.96. So you can see this, I am just showing you, of course any of you can see it easily because just Google here the tables of the standard normal distribution. So corresponding to 0.975, you can see it is 1.96. Okay, that is the point. So you can easily just find it out. So this gives us 4a is equal to 1.96, which means a is equal to 0.49. So what is the interval? 10 minus a to 10 plus a. So the shortest interval is 9.51 to 10.49. This interval has the probability 0.95. Is this example clear?
Yes, sir.
Yes, sir.
Okay. Now another thing is there. Actually, I mean, the way I have given the normal distribution, I wrote the density function and I have derived certain things. But actually, normal distribution arises naturally as a phenomena for various things. And one of the most significant things is that if I consider several observations, and they may be from any distribution, like they can be from binomial distribution, they can be from exponential distribution, they can be from Poisson distribution, but I consider the average of them. Okay. Now, why do I consider the average? So you look at our real life applications of the data, how the data is used, how the data is utilized. So for example, you want to find out average price of a certain item, isn't it? Or for example, average sales, average marks, like even your CGPA is an average, isn't it? Because you are considering grades of various subjects, then the points of all of them are added and then divided by the total credits, and that is why how you get the CGPA, isn't it? Cumulative grade point average. So in real life, we always tend to use averages. We don't use single observation, isn't it? How do you come across that what is the price of a wheat, or what is the price of potato, or what is the outcome of certain match? So it is based on the sum of the observations or the total or the average. So for example, different players score different, for example, in a game of basketball or in a game of cricket, but the result is determined by the total. It is not determined by single players thing. Okay. So that means we are always interested in the totals or in the averages. And there is a very strong result which is called the central limit theorem, which says that let us have observations from any distribution, but if I consider the sample mean, it will be approximately normally distributed if the sample size becomes large. Okay. I will give you the formal statement of this after some time, but let us take up two special cases. So for example, if I am having a binomial distribution, or if I am having a Poisson distribution, then what happens? So first of all, we prove these basic central limit theorems, and then the general central limit theorem I will prove after some time. Okay. So the normal distribution arises as an approximation of a binomial under certain conditions. So I will give you some of these basic results here. So first I consider Poisson approximation to normal. So let X follow a Poisson distribution with parameter lambda. Okay. Then as lambda tends to infinity, the distribution of Z, that is x minus lambda by square root lambda, converges to normal 0, 1. Okay. Let us look at the proof of this. I mean, these are these are some of the basic limit theorems. Okay, this is known as de Moivre-Laplace. This is named after de Moivre-Laplace limit theorem. So let us consider the moment generating function of so that is equal to expectation of e to the power t z, that is expectation of e to the power t x minus lambda by root lambda. That is equal to, so let us do some sort of simplification here. Okay, so this is then e to the power minus t root lambda, and then it becomes expectation of e to the power t by root lambda x. Is that okay? Is this clear?
Yes, sir.
So this is nothing but the moment generating function of x at the point t by root lambda. X is a Poisson lambda distribution. What is the moment generating function of a Poisson distribution? It is e to the power lambda e to the power t minus 1. Do you remember that? It is e to the power lambda e to the power t, so t by root lambda minus 1, because t is replaced by t by root lambda here. Is that okay?
Yes, sir.
So we just try to write down the terms. What are the kind of terms that we are having? So e to the power, this t by root lambda, we give a expansion here. So this becomes 1 plus t by root lambda, t square by 2 lambda plus t cube by 3 factorial lambda to the power 3 by 2 plus and so on minus 1. Okay. So that is equal to, now you look at the terms here, the 1 gets cancelled out, then you get lambda t by root lambda, so it becomes t root lambda, and this is minus t root lambda, that also gets cancelled out. So you are left with e to the power t square by 2 plus, now you have terms 1 by lambda to the power 3 by 2, so it becomes 1 by lambda to the power half, okay, 1 by lambda to the power half plus some terms, okay. So if I take the limit as lambda tends to infinity, if this goes to e to the power t square by 2. This is nothing but the MGF of a standard normal distribution. Which is MGF of a normal 0-1 distribution. So again, by the uniqueness property and the continuity property of the convergence, we conclude that x minus lambda by root lambda has a limiting normal distribution. That means we start with any Poisson distribution. And now, of course, let us relate with whatever statement I gave earlier. I said that if I am considering the sums or the averages, then they tend to converge to have a normal distribution. So the Poisson distribution, what is the Poisson distribution? It is the number of occurrences during a time interval or in a particular area or in a space. So basically there are several things happening and you are actually taking the total number. So it is actually sample sum. So here we have proved that the sample sum converges to normal distribution. This is of course for the Poisson process. We will do it for say binomial also, and then we will do for general also. That we will see later on. Okay. Let us have a break for 5 minutes and then we again meet.
Sir, can you please tell us about the test that was scheduled tomorrow?
Somebody is saying something?
Yes, sir. Yes, sir. I was asking about the test that was scheduled tomorrow.
Yeah, I
So,
announced now that test will not be there tomorrow. I will fix another alternative date. Okay.
okay, sir. Thank you.
Yeah, tomorrow's test will not be possible because the convocation is there. So there may be some network issues and all, because that event is also being done online with more than 3,000 participants. And here also 1,000 students are there. So therefore, it is not possible to conduct the test tomorrow. So we'll give another date. Okay. Okay, so we proved one central limit theorem.
Excuse me, sir. Excuse me,
Yes.
sir.
Yeah.
Sir, I had one request. Could you allow us to review our answers for the class test?
Okay, it has not been shared till now. Has it not been shared till now?
Sir, no, we cannot view our answers.
Okay, then I will ask. Okay, I thought he has already shared. Okay, I will ask them to share. Okay, fine.
Thank you, sir.
Okay. Let us look at the second central limit theorem, which is one of the basic ones. So again, if you look at the binomial distribution, what is a binomial distribution? It is the total number of success in a given number of trials. So you are actually adding the terms, isn't it? In each trial you get a success or failure, and then you are looking at the total number. So that is also a sum. So our second central limit theorem is also this is about binomial distribution. So let us consider, say, x follows binomial NP. We have seen that as n tends to infinity and p tends to 0, such that NP tends to a fixed number, then the binomial distribution converges to a Poisson distribution. But we have now seen that as lambda tends to infinity, then Poisson converges to normal. So in binomial distribution, if n becomes too large, that means NP whatever be that, but if NP is also becoming very large, then binomial distribution also converges to normal distribution. So let us look at this. So let us put, say, z is equal to x minus np by root npq. So as n tends to infinity, the distribution of z converges to normal 0, 1. Okay, so this is the second central limit theorem. Of course, again it is called, it is named after Bernoulli and Riemann and Laplace, etc. Let us look at the proof of this. So that is expectation of e to the power t x minus np divided by root npq. So this is equal to e to the power minus npt by root npq into expectation of e to the power t by root npq into x. So that is equal to e to the power minus npt by root npq mx t by root npq. Because this is the moment generating function of x at the point t by root npq. You know the moment generating function of x in the binomial distribution? Do you remember that? Any student remembers that? What is the moment generating function of a normal distribution? No student remembers? Shall I call the names?
So expectation of e to the power lambda t.
What is the MGF of a binomial distribution? Let me ask some person. I can see the name Naman Jajani. Do you know the moment generating function of a binomial distribution?
Yes, sir. But sir, I don't
What is
remember
that?
formula exactly. But sir, yeah, I have studied, sir.
Okay, let me ask someone. Neha Dalamia.
No, sir, I don't remember.
Muskan Jain. Muskan Jain. Rishabh Goyal.
Yes, sir. It is q plus p e to the power t whole power n.
NPT by root NPQ, then Q plus P e to the power T. So T is T by root NPQ whole to the power N. Okay. So now actually I have to take the limit of this as n tends to infinity. But as you can see, the terms are little bit complex terms here, because e to the power certain terms you are having where n is coming, and then it is multiplied by certain term where n is coming, and then it is raised to the power n. So again, there are multiplicity of terms. So it is better to simplify this. We can take log on both the sides. So this will give me minus npt by root npq plus n times log of this term. So this is actually 1 plus p e to the power t by root npq minus 1. Okay. I have written q as 1 minus p, and then I have adjusted the term. So this has certain advantage. So this is minus npt by root npq plus n log, and let us look at this inner term here, 1 plus p, and let us expand this e to the power t by root npq. So that gives us 1 plus t by root npq plus t square by 2 npq plus t cube by 3 factorial npq to the power 3 by 2 plus and so on minus 1. Is that okay? I have just used the direct expansion of e to the power t by root npq. So here 1 gets cancelled out, and you are getting minus npt by root npq plus n times log of 1 plus p, and we get all this term t by root npq plus t square by 2 npq plus and so on. Is that okay? Is this simplification clear to everyone?
Yes, sir.
Yes, sir.
You look at this log of 1 plus something is there, but that plus something in the denominator you are always having n there, and we have to take the limit as n tends to infinity. So that means this term can become very small. So if it becomes small, because for expansion of log of 1 plus x or log of 1 minus x, what is the condition? That x should lie between minus 1 to 1. So for n large, this can be expanded. So for large n, we can expand using the expansion of log 1 plus y. Okay. So what is that? That is equal to minus npt. We have to write the terms a little bit carefully. Plus n times log of 1 plus x is x minus x square by 2 and so on, isn't it? So here the term is p and all that. So it becomes p t by root npq. So I will write as it is whatever terms are coming. Plus t square by 2 npq plus t cube by 3 factorial npq to the power 3 by 2 plus and so on. And then you will have plus p square by 2 t by root npq plus t square by 2 npq plus and so on whole square. Sorry, this will be minus sign here. There is a minus sign here and so on. Okay. So let us do the simplification. Is this step clear to everyone?
Yes, sir.
You look at the first term here inside the first bracket here. So you get npt by root npq with a plus sign, and there is a minus npt by root npq, so that gets cancelled out. This term and this term get cancelled out. Then you get the next term. In the next term, n gets cancelled out. This p gets cancelled out. So you get t square by 2q. Because this np gets cancelled out, you get t square by 2q. And then you have other terms. In the next term, n to the power 3 by 2 is there in the denominator. It is multiplied by n. So that means in the denominator, I will get n to the power half. And then thereafter, larger terms will be there. So I will not write that because finally we have to take the limit of this as n tends to infinity. So those terms will vanish. Let us look at the next term. In the next term, the first term will be square of this, that is t square, and then divided by npq. So there is an n here, that n will get cancelled out. This p will remain there. So p t square by 2q. And thereafter, any term will contain a power of n in the denominator, because even this cross product term, that will have n to the power 3 by 2. So n is here, so n to the power half will be there. So you will have plus 1 by n to the power half, and other terms will be there. So as n tends to infinity, these terms will vanish. So if I take the limit, then I will be left with only these two terms, which is nothing but t square into 1 minus p by q, and that 1 minus q and p will get cancelled out. So you get only t square by 2 as n tends to infinity. So mzt converges to e to the power t square by 2 as n tends to infinity. So this proves that the distribution of x minus np by root npq converges to normal 0, 1 as n tends to infinity. So these are some of the basic limit theorems, but it also tells lot of good things about the normal distribution. That normal distribution is basically arising as a limiting distribution of the sums, limiting distribution of the means, and so on. Because of the linearity, immediately mean will also be valid. So let me just take up one or two exercise here. Is the proof clear?
Yes, sir.
If I keep the test on 6th March in the afternoon, is it that okay to all of you? At 4 o'clock?
Sir, could you tell the day on which 6 March is?
Just check it. It must be Saturday. Is it Saturday?
Yes, sir, it's Saturday.
Sir, like
So Saturday at 4 o'clock.
for chemical engineering students,
Yes.
like, due to some issues, our sir doesn't take classes on the weekday, so we shifted to Saturday. So is it possible that
At what time?
from 4 to 6? So is it possible that we have a test at 3 or before?
Yeah, we can have 3 o'clock. At your EA activity gets over at what time?
At maximum 12 or 1, sir.
So 3 to 4 we will keep.
Yes, sir.
See, if
And
that
sir,
is okay
so will the syllabus be the same?
Yeah, for this one we had announced, it will be basic, this PDF, CDF, PMF and all those things, moments,
discrete
MGF
distribution.
and the discrete. Yeah, we'll have the same, yeah.
All right, sir.
So is that okay, 6th March? Then I will announce in all, I will ask other professors to announce in all their sections. Okay?
Yes.
6th
Sir.
March at 3 to 4.
Yes, sir.
Okay? Okay. So the probability that a patient recovers from a rare blood disease is 0.4. What is the probability that less than 30 survive? So if I consider X as the number of survivors, then X is having binomial distribution with 100, because we have considered total 100 persons here, and the probability of recovery is 0.4. So P is 0.4 here. So this is binomial NP. But here you can see that N is large, but P is not small. Okay, P is also large. P is 0.4. I mean, it's a normal value. So NP becomes 40. So it cannot convert. I mean, if you take Poisson approximation, it is not at all good. Okay, so we go for the normal approximation. So if we go for the normal approximation, so let us look at it. NP is equal to 40. What is NPQ? NPQ will become 24. So root NPQ, that is equal to, okay, 4.899 kind of thing. Okay. So X minus 40 by this 4.899, this is approximately normal 0.1. We will use this. What is the question asked? Probability of X less than 30. So, okay, this is another thing, because we are approximating a discrete distribution by a continuous distribution. So this is creating another kind of problem. In the discrete distribution, probability that X is less than 30 or probability X less than or equal to 30, they are not same. In the continuous distribution, they are same. But in the discrete distribution, X less than 30 and X less than or equal to 30, they are not the same. Okay, because if you consider, say, a discrete distribution so if I say, suppose this is a point M and this is M plus 1. So if I am saying x less than or equal to M or x less than M plus 1, okay, they are not the same, isn't it? Because additional probability has been put here. So if I am approximating it by continuous distribution, a wise approach is to take the midpoint of this one, okay. So we take M plus half, okay, we take M plus half here. So we approximate it by probability x less than or equal to 29.5, because see here this can be written as x less than or equal to 29 or x less than 30, okay, both are same. So in the continuous case we put the mid value here, okay. This is called continuity correction. And then next what we do, we just approximate z less than or equal to 29.5 minus 40 divided by 4.899. So that is probability z less than or equal to minus 2.14. So from the tables of the normal distribution, again you can see easily this value is 0.0162. So there is approximately 0.016 probability that less than 30 will survive. Is that okay? Could you understand this approximation? Since in the normal distribution you are having 100, so if I want to calculate directly that probability in the binomial distribution, what will I have to calculate? I will have to calculate something like 100 Cj 0.4 to the power j, 0.6 to the power 100 minus j. J is equal to 0 to 29. This one would have been the exact number. But as you can see, because of the factorials and then the powers involved, it will include lot of approximation errors. So this will not give the result to the accuracy which is desired. But if we use the normal approximation, we get the results very quickly and nicely. Is this clear?
Yes, sir.
Let me give one example of the Poisson approximation to normal. Okay, suppose thefts occur in hostels like Poisson process with lambda is equal to half per day. That means monthly it will become 15, okay, on the average. So just I am asking some questions. What is the probability of not more than 10 thefts in a month, not less than 17 in a month, and so on. So if you want to calculate using the Poisson distribution, it is e to the power minus 15, 15 to the power j by j factorial, and you have j is equal to 0 to 10 or other one will become j is equal to 17 to infinity and so on. As you can see, again, because of the large scale approximations involved, there is a lot of computational error coming if we do the calculations. So let us use the normal approximation here. So for a month, your lambda is equal to 15, which we consider to be large. So you will have x minus 15 by root 15, approximately normal 0, 1. So the first one is x less than or equal to 10. Again, we use the continuity correction here. So this we write as x less than or equal to 10.5. Okay, because it is same as x less than 11. But in the discrete case, the two things are different. So we take the mid value here. So this is probability x minus 15 by root 15 less than or equal to 10.5 minus 15 by root 15. So that is phi of minus 1.16, which you can easily check from the tables of the normal distribution. It is 0.123. Up to 2 decimal places, this is accurate even if you calculate directly using that e to the power minus 15 and that formula. So that means this is a very good approximation. Actually, the difference is only 0.005. Similarly, let us look at x greater than or equal to 17. So of course, you can write it as 1 minus probability x less than or equal to 16. That is 1 minus probability x less than or equal to 16.5, because we apply the continuity corrections here. That is z less than or equal to 16.5 minus 15 by root 15. That is 1 minus phi of 0.39. So you can check the value from the tables of the normal distribution, and this is 0.3483. From the tables of if you do the direct calculation of this one, then you will see that the error is only 0.002. So this is very good approximation here also. And this is extremely simple because you can just finish the problem in few seconds. Whereas if you use the direct calculation for this Poisson probability, then either you have to use a small computer program, or if you are using a calculator, then you have to do large scale calculations. And in the calculator, the errors will be compounding, and therefore you will have compounding computational errors. Is it clear? Is the problem clear to everyone?
Yes, sir.
Are you hearing? If y follows normal mu sigma square, then x is equal to e to the power y is said to have a log normal distribution. So what will be the probability density of x? That will become 1 by sigma x root 2 pi e to the power minus 1 by 2 sigma square log of x minus mu square. Here x of course has to be positive, mu is real, and sigma is greater than 0. That means if x has a log normal distribution, then log of x has a normal distribution. Okay, so that is the relation between normal and a log normal distribution. If you want to calculate the moments of log normal distribution, then just use this relationship. This is nothing but the moment generating function of a normal distribution at t is equal to 1, which is nothing but e to the power mu plus sigma square by 2. Similarly, if I consider, say, expectation of x square, then it becomes expectation of e to the power 2y, which is nothing but the moment generating function of the normal distribution at t is equal to 2. So it is e to the power 2 mu plus 2 sigma square. So variance of x becomes expectation of x square minus expectation of x whole square. So it becomes e to the power 2 mu plus sigma square, e to the power sigma square minus 1. So in fact, you can write moment of any order because it is nothing but the MGF of a normal distribution. If I want to write down mu k prime, that is expectation of x to the power k, it is nothing but expectation of e to the power ky. That is the moment generating function of y at k, that is e to the power mu k plus half sigma square k square. So for a log normal distribution, the moment of any order can be calculated. So this log normal distribution, is it clear? So basically it is an exponential transformation of a normal distribution, or you can say normal distribution is a logarithmic transformation of a log normal distribution. So many times when we consider the original observations, they may not be very convenient to use. So if you take e to the power or if you take log of that, then during this COVID times, you might have noticed here when they are talking about the trend, then they have shown the logarithmic curve as well as the standard curve. So why so? Because the values were ballooning, the skyrocketing. I mean, if you look at the data from John Hopkins and if you look at the worldometer and so on, then you will find that because if you look at the whole world, then the number of cases, the number of death cases, they were very large. So they took log of that. So that's why they were showing logarithmic trend. So these are all standard practices which are used. Let me just give one example of application of log normal distribution. So x is a normal distribution and it has mean 7.4 through and variance is 0.56. You have to find the probability of x greater than 8. Okay. So we use the information that is given here. It is given that mean, that is e to the power mu plus sigma square by 2, that is 7.43. So mu plus sigma square by 2 is log of this, which is nothing but 2.0055. Okay, that is one equation. Similarly, variance is given. So we have just now seen the formula for the variance also. So basically variance is nothing but mu 2 prime plus mu 1 prime square. So that is e to the power sorry, minus. So this is minus here. So mu 2 prime is equal to mu 2 plus this mu1 prime square, that is 7.43 square. Okay, and this is 0.56. So this also let me write here. Okay, so mu2 prime was e to the power 2 mu plus 2 sigma square. So that gives me 2 mu plus 2 sigma square is equal to 4.0211. So you can just solve this equations number 1 and 2. You get mu is equal to 2 and sigma is equal to 0.1. I mean, this is approximated value. I have just written because it is 2.00 something, and similarly this sigma is 0.100 something. So now probability x greater than 8, this is nothing but probability of log of x greater than log of 8. So what is the distribution of log of x? Log of x follows normal with mean 2 and sigma square is equal to 0.1 square. So we transform this to the standard normal distribution. That is probability z greater than 0.79. So you check the tables of the standard normal distribution, that is 0.2148. So log normal distribution is very closely related to the normal distribution, and any probability statement of the log normal can be calculated using the normal distribution. Okay, so I will stop today's class at this point of time. Tomorrow the class will not be there due to the convocation here. I will ask this person to circulate the marks of all the students. Okay.
Sir.
Yeah.
Sir, can you read my message once I have posted in the chat? Actually, I won't be available on March 6th for the exam.
Why?
Actually, I have a journey, sir. It's a family trip to Tirupati. So I'll be on a train at that time.
So if that is there, then see, we are conducting 4 tests. We have announced that we will take the best 3. So if somebody is not appearing, then you don't appear. What we can do? Because there are 950 students here. If we go for everybody's convenience, then it is very difficult. So if you want to miss, you miss it. What we can do? Okay.
Yeah, okay, sir. It's best 3 or 4.
Or if you
right,
somehow
sir?
in the train also, if you can take somehow, then it is okay. Otherwise, you have to miss it.
There will be no problem even if I miss the test, right, sir?
Yeah, I mentioned to you that we are taking 4 tests and we'll take the best 3.
Okay, then it's fine, sir. Thank you. Okay.
Okay, so we stop the class today. Tomorrow there is no class and we will meet the next one. But I will circulate the assignments and I'll ask this person to circulate the marks also in your first test. Okay. Okay.
Excuse me, sir, marks has been circulated.
Sir, also
circulated. Somebody is telling some not circulated, somebody is telling circulated. So
marks has been circulated, but
no, sir, we were asking to open the review option in Moodle. Like there is a review option in Moodle where we can check the answer for the individual question.
Okay.
So the review option in Moodle could be open.
Okay, that I will ask this gentleman to do that. Okay, fine. Okay. We will do that. Okay. Okay, so shall I close? Okay.
Okay, sir. Thank you, sir.
Okay.